welcome to our last, but by no means least, CAMS colloquium for this academic year. And we're delighted to have Bjoern Bringmann from Princeton, who will talk to us on global well-posedness of the stochastic Abelian-Higgs equations in 2 dimensions. So thank you very much, Bjoern.
Well, thank you very much for the invitation. I'm very happy to be back in LA. Yeah, so as Susan already said, I'll talk about the global well-posedness of the stochastic Abelian-Higgs equations. And everything that I'll speak about is joint work with Sky Kao, who is currently a postdoc at MIT. Let's take a quick look at what we've planned for today. So I'll start this talk with a little bit of an introduction, which will take maybe 20 minutes or so. And I'll tell you a little bit about Langevin equation, and later about this Abelian-Higgs model, just kind of the start of today's talk. I'll then tell you what the results are that people came before and that we were now able to obtain. And in the end, I'll try to give you an overview of the argument, but let me already promise you that I won't touch any of the technical details because that would be way too much, right? So let's start with an introduction. So I want to talk a little bit about Langevin equations. This will first be in a finite dimensional setting, but later on everything will be infinite dimensional because we'll talk about PDEs, right? So for now, let's start with an energy functional, which I call E. And in this introduction, this will be a function from Rn into the non-negative numbers. And you need some conditions on it. You typically want it to be somewhat smooth, so let's say C1. And you want it to have a little bit of growth. So you want it to be coercive, but I don't want to make this super precise here. Now, once you have such an energy, you can define a Gibbs measure, which is a probability measure on Rn. And this is defined as follows. You have some normalization constant here, Z inverse, which is supposed to normalize the mass, right? So it's supposed to make it a probability measure. You have an e to the minus the energy. And then you have dq, which stands for the Lebesgue measure on RD, or on Rn here. And at least if your energy has a little bit of growth, it's clear this is a nice, well-defined probability measure. Okay. The last limit we have here is the Langevin equation, which is a stochastic differential equation. Right. So here's a little bit of a conflict of notation. This dq here is the Lebesgue measure. This dq of t is the e to differential of a stochastic process, q of t. But that's the common notation for both of those. And so what is the stochastic differential equation? I have 2 different terms on the right-hand side. I have the first one here, which is a drift term that contains the negative of the gradient of this energy E, right? And if I only had this part of the equation, I would be a gradient flow. But then there's also this stochastic term here, which is this derivative of a Brownian motion B. So this is wide in time noise, right? So this kind of adds randomness into this system. So the maybe most well-known case of this is when you have an Ornstein-Uhlenbeck process, which is one of these kind of stochastic processes right here. And this corresponds to the case when your energy is kind of the nicest it could possibly be, which is the quadratic function q squared. And in this case, you can, of course, work out what this Gibbs measure is, and you just get a Gaussian measure with mean 0 and variance 1. Now, I realize that not everybody in this room necessarily works with SDEs. So I also kind of plotted a sample path of a solution to this SDE, right? So if you zoom in anywhere here, it pretty much looks exactly like Brownian motion. So on very small scales, all you see is this kind of stochastic process. But then on large scale, this actually behaves very differently than Brownian motion, right? So as many of you might know, Brownian motion typically grows like square root of t, whereas this here actually does not grow at all. At least on average, it's going to be of size 1. So these 2 objects that I had are, of course, somewhat linked because they were defined using the same energy, right? I defined the Gibbs measure and the Langevin equation using the same energy. But there's also a more explicit link, which I have here as a theorem, and I just refer to this as invariance. And it tells you that this Gibbs measure mu that we just defined is invariant under the Langevin dynamics. And because, again, I realize that not everybody here works with SDEs, let me also put this into slightly different words that maybe some of you might find more helpful. And maybe some of you might find less helpful, but let's hope it's the former. So let's take our Q0, which is the initial data of this SDE, and our B, both of which will be random. Okay, and let's assume that they're independent, probabilistically speaking. So the initial data is independent of stochastic forcing, which is a very natural assumption one could be making. I already know that the B is going to be a Brownian motion, so I know that law. And let's assume that the law of the initial data is given by this Gibbs measure mu. So I sample my initial condition from this measure. Right? And then what this theorem tells you is the law of the solution, the law of q of t, is still going to be given by this measure for every time t. right? So even though the SDE kind of clearly evolves in time, that's what we saw on the last slide, right? The law of the solution does not change, right? And this is what's an invariant measure. Okay. So because of this kind of theorem, we have this link between the measure and the equation. So if you understand the measure extremely well, you should be able to leverage this and learn something about the equation. But conversely, if you know the equation, you should also be able to learn something about the measure, right? So there's usually this back and forth relationship between the two of those. Many of you might think of the measure as being maybe easier than an SDE. But actually, a lot of the things that we'll discuss in this talk are exactly of the opposite direction. So we'll be mainly interested in the direction going from right to left. We'll try to kind of understand this equation very well, and then we'll try to get some information about this Gibbs measure using the equation. And this is typically referred to as stochastic quantization, which is something that was introduced in the physics community first by Parisi and Wu, and nowadays has a lot of different applications. Right, so we'll see at least in one example how this can be done here. Okay. So this, I think, finishes my introduction of this Langevin equation. And let me now introduce kind of the other main star of this show, which is the Abelian-Higgs model. So, and of course, I'm not assuming that you've seen this at all. So the one unfortunate thing is that I need to introduce a little bit of notation, which I put on this slide, but I fully understand that once the slide is gone, the notation will be gone from your heads. So let me also kind of copy this down on the blackboard so that you can refer back to it during the talk. So the first disclaimer, which I don't think I have to copy, is that most of what we'll say will be in the periodic setting. So everything will be on a torus, right? So not in Euclidean space. I have a dimension, which I'll call D. And for now, this could be anything bigger than 1, although later on, the main result will be in dimension 2. Okay. Later on, we'll need to specialize. I have a connection 1 form, which I denote by A. So I have this connection 1 form. A, which goes from TD into RD. So I'm just viewing this as a function that takes values in an D, or alternatively as D different functions that take value in R. So the reason why I'm referring to this as a connection 1 form is because if I were an actual differential geometer, like at least one person in this room maybe, the way to write this would be that you should write A of x is AJ of x dxj. That's kind of the correct differential geometric interpretation of this object. But at least for this talk, it will be more convenient to think of it as just D different R-value functions. In addition to this, I also have what is called the Higgs field. And I'll sometimes just call this the scalar field because that's what it is. And this is a map phi, which goes from TD into C. Okay, so it's scalar, but it's complex valued scalar. So far, I haven't really made any definitions. I've just introduced the names of variables, right? So now here comes my first definition, which is what a covariant derivative is. Okay, so covariant derivative. And this should remind you of something that maybe you've seen in differential geometry or in Riemannian geometry. And the way this is defined as follows. I have dAj of phi. So here, j is not a power, it's just the direction in which I take the derivative. So it's one of the d different coordinates. And the way it's defined is as follows. I have delta j of phi, which is just the derivative in the jth coordinate, the classical one. But then I also add this 0th order term, which is iaj of phi. So I multiply kind of by one of the components of this connection 1 form, and I have this I, so the complex unit. So that's my covariant derivative. And the last thing that I'll need here is the curvature tensor. So the curvature tensor is a 2 tensor. So this is FAJK. And it's defined in terms of A. And it's this curl-like quantity here, right? So maybe the first comment regarding this definition is that I get this very nice formula, which I wrote on the bottom of this slide right here. So the left-hand side has this difference of, two differential operators acting on phi. So I have dAj, dAk, minus dAk, dAj. So this is really the commutator of these two covariant derivatives, and it acts on phi. And then, the Euclidean derivatives, of course, commute. But these covariant derivatives do not have to commute. So on the right-hand side, I get I, F, A, J, K, and phi. right? So this curvature tensor captures the lack of commutativity of these covariant derivatives. And that's really what curvature is supposed to do. It's supposed to capture lack of commutativity of derivatives. So this is very, very natural. So this is something you can quickly calculate. It's takes about a page or maybe slightly less. Just to highlight this, there's no second order terms in phi on the right hand side. That's maybe not so surprising because the usual Euclidean derivatives commute. But actually the first order terms in phi also cancel. And the only thing that survives are terms that are zeroth order in phi and first order in A. Right? So there's a lot of cancellation going on the left hand side here. Okay. So now I have all of these different differential geometric objects. And I can now define an energy functional, which is rather natural. And maybe I should also be writing this down. So this energy is defined in terms of A and phi. And it's an integral over this torus. And what I'm integrating the square of the size of this curvature tensor. And it's convenient to put a 4 here in order to. Then I have the size of the covariant derivative of phi. So you should think of this as some kind of H1 norm, but it's not an H1 norm in terms of the usual derivative, but of the covariant derivatives, right? So it's defined using this dA. And then I have a quadratic term. So I have a phi to the 4 over 4. Okay, and this is kind of the energy functional, which we will care about in this talk. And at least if you take these kind of differential geometric objects for granted, it's a very natural quantity to be looking at, right? So you're measuring kind of the curvature here, and you're measuring the usual kind of H1 norm, but in a covariant way of these kind of scalar fields. So what we want to do is we want to study the Gibbs measure and the Langevin dynamics corresponding to this energy. Yeah.
So is there any motivation to consider the force power?
So that's the one that appears in physics, I think. So often you have this kind of double well potential. Although here, because we're in infinite form, it doesn't make any difference. So this is, I think, the natural one that you would see in physics if you have scalar fields. And it's nice for the proof, actually. So maybe already foreshadowing this, the main result I'll state, if you leave this out, it doesn't work. So this will be important, actually, for the main result. Any other questions so far? Are the definitions clear? Because if they're not, things will go downhill from here very fast.
Oh dear.
Okay. Yeah.
Is this, can we think of this like the phi being the scalar Higgs field and the A being an electromagnetic?
Yes. So in fact, I'll say at some point that the physical motivation of this is quantum electrodynamics. And then A would be the electromagnetic field, and phi would be kind of, let's say, a charged particle inside this electromagnetic field. Okay, so we want to study this, and okay, I'll get to the motivation a bit later. I first wanted to give you this. But before we can actually write on this measure and the Langevin dynamics, I have to do a slight detour, which is into gauge transformation and the Coulomb gauge. So let's bear with me for a second. So I have this function theta here, which is the only function in this talk which by itself does not necessarily have to be periodic. But I'm assuming that the gradient and e to the minus I theta are periodic. So actually, if you're very quick, the second one implies the first, but I wrote on both. So what this tells you is that theta, even though it doesn't have to be periodic, it's a function that is the sum of a periodic function and a function of the form n times x, where n is an integer vector. And if you have such a function, you can define the following gauge transformation, or let's say change of variables. You change a and phi into a theta phi theta, where you add the gradient of theta to a, and you multiply phi by e to the minus I theta. Okay, this is a somewhat natural change here, and you can motivate this by, if you view everything in terms of vector bundle and so on, but I didn't want to go too far into the differential geometry. So I'm just giving it to you here. And it turns out this is really a symmetry of our model. So everything that I wrote on the blackboard so far transforms very, very naturally under this change of variables. So for instance, if you compute dA theta of phi theta, you just get e to the minus I theta of the original one. And the reason for this is at some point, the Euclidean derivative inside here will hit the exponential factor inside here, but this is canceled exactly by the term that I added to A. Right? So the only thing that you get is this thing here that walks out. And then the other thing that's true is that if you look at the curvature tensor of a theta, it's the same as the original curvature tensor. And that's just because the curl of a gradient is 0. So because of this, for instance, this energy doesn't change if you gauge transform. So the energy of a theta and phi theta is exactly the same as the original energy, because this is exactly the same. This only changes phase, but once you take absolute values, it's gone. And the same here as well, right? So this is really a symmetry of your energy. The energy doesn't change. And that is actually very bad news, because it tells you that the energy is very, very degenerate, right? So let me remind you of something that I'm sure most of you know, right? Many PDEs have symmetries, right? The most common one is maybe translation symmetry. And sometimes it's an issue, but most of the time it's fine. And the reason why it's fine is because the translation group is a finite dimensional thing, and it's typically just RD, right? But here, our group of symmetries is something much bigger, because it's the group of all of these functions, which is an infinite dimensional thing, right? So, having control of this energy gives you almost no useful control of a theta and phi theta, because, anyone you have in a sub-level set, you can transform with this whole group, right? So it's really bad if you want to get any useful bounds on a and phi. But there's one saving grace here, which is that when you actually study these models in physics, you don't really care about the state a and phi itself. You really only care about, the equivalence class, right? So you don't really want to distinguish between this one and the gauge transform one, because you really view these as equivalent. One of the reasons for this is that every one of the physical observables that you would care about is actually invariant on this gauge symmetry, right? One of the observables for which this is true we've already seen, and that's the energy, right? So because of this, it makes sense to, not really work with the states themselves, but to really work with the equivalence classes. And to be honest, not even with the equivalence classes, but to just pick certain representatives of these equivalence classes which you like, and then work with those representatives, right? You're just going to fix one of those. And this is typically called gauge fixing, right? So now you have a choice to make in terms of like which representatives you like. So there's different ways to impose what's called a gauge condition. The most classical one is what's called the Coulomb gauge. And this is also the one that we'll use in this talk, right? So we'll impose this Coulomb gauge condition, which is that delta J AJ, where the J is being summed over. And we just say that this has to be equal to 0. And this almost fixes the gauge. So there's a little bit of an issue here, because if you compute the divergence of this gauge transform field, you'll get the Laplacian of theta. And the Laplacian on the torus has a kernel, right? It's the constant functions and it's the linear ones. But that's a little bit of a technical issue that I want to avoid in this talk, right? So because it's only a finite dimensional kernel, it's not that big of a deal, but sometimes you have to address it. But it's a talk, right? So I'll ignore that. Right? So just think of this almost as being not here, right? So think of this as actually really fixing the gauge. Right. So now we'll work in this kind of Coulomb gauge. So everything that I'll say from now on will be for connections that satisfy this condition. So now that we have this, we can write down the Langevin dynamics associated with energy. Right. So formally, it looks the same as what we saw earlier. It's this kind of gradient flow, but with the stochastic forcing added to the right-hand side. Right. So here's the two equations. That's maybe the last thing that I'll copy on the board, because these are also somewhat hard to remember. So the equation for A looks as follows. I have delta T of A is the Laplacian of A minus P dot. So this is my notation for the Leray projection. It's a little bit non-standard, but we also needed P for probabilities, and we needed for little Rayleigh projections. And that's kind of the one that got left. So this is my notation for Leray projection, which, as you maybe know, it's a projection onto divergence-free vector fields. Right, so it's natural because we want to stay in this Coulomb gauge. So we have that here. And we have this Leray projection of the imaginary part of phi bar EA phi. Okay, and then we have the stochastic forcing. So we have another Leray projection of psi. And psi here is a space-time white noise. Right? So it's a Gaussian random distribution whose correlation function are Dirac deltas. Okay, I'll say more about this as we progress. Right. And then I have an equation for the scalar field, and it looks as follows. I have a delta T of phi, dA J dAj. And here I'm raising and lowering indices with respect to the Euclidean metric. So I just like that whenever I sum over something, I want it to be once upstairs, once downstairs to follow the convention. So that's why I'm writing it like this, but they're exactly the same. And then I have phi here, and then I have minus something cubic. And then I have a zeta, which is also a space-time white noise. So the difference here is that this is an RD valued one, and this is a C valued one. But other than that, they're the same. And that's my equation, right? So this here, everything up to here and here is kind of the gradient of this energy, as long as I'm in the Coulomb gauge at least. And this here is this kind of stochastic forcing. So it's the analog of the D of B that we saw at the very beginning of this talk.
Yeah, this is why you have phi to the 4 in the energy, right?
Yes, yeah. So the phi to the 4 gives me this cubic term here. Without the phi to the 4, I wouldn't have the cubic term, and the cubic term, as we will discuss, is very useful. So what are the difficulties here? So if you have space-time white noise, it's not so hard to figure out what its regularity is. If you count things parabolically, these kind of space-time white noises, they have regularity -1 minus the dimension over 2 minus epsilon. And this turns out to be very, very low. This is very negative. And at this regularity, making sense of this SPDE here is quite difficult, and we'll talk about that. And just one disclaimer, because of this low regularity, we often have to add certain renormalization terms here. So these are counter terms that kill certain ultraviolet divergences. That's something that the physicists have been doing for decades and now has a rigorous mathematical underpinning. But this is something that's a little bit orthogonal to the main points I want to discuss. So I want to sweep this under the rug as best as I can. Right? So occasionally I think there will be a little bit of a white line in some of the later slides. But modulo these renormalization terms, I think I'll say will be correct. Okay. So that's the model. So now that I told you about this model, I should tell you a little bit about the significance of this Abelian-Higgs model, because otherwise you might ask, well, why should I care? Right? So let me give you 3 different reasons. The first one is mathematical. So let's say, one day of your life, you wake up and say, I would like to study a problem that involves PDE, probability theory, and differential geometry. I don't know if this will ever happen to you, but let's just condition on that. And I think then this is a very natural starting point. So there are many other problems you could study that kind of fit this bill, stochastic versions of the harmonic map heat flow, stochastic wave maps, Yang modes, which I'll discuss in a second. But this is one of the most natural candidates, and it's in some sense maybe even the easiest one. So it's a good one to start with. The second one is physical, and this already came up. So this model appears in quantum electrodynamics. So if you want to quantize electrodynamics, that's one of the ways to do it. So this is kind of why you care about this energy specifically. However, I would like you to not press me on this because this is about as much as I know about the physics. So feel free to ask me about the PDE, probability theory, and differential geometry in that order, actually. But please don't ask me about the physics. Okay, and the last one I want to mention is that this Abelian-Higgs model is kind of a special case of a slightly more famous model, which is called the Yang modes model. So you may be aware of the fact that this is the Yang modes millennium problem, which is, of course, a very famous problem. And a lot of the things that I'll discuss are actually very, very motivated by this. Now, I haven't really introduced this Yang modes model because it would require a bit more notation than I already have. But as I said, you should think of this Abelian-Higgs model as a special case of this Yang modes model. So why is it a special case? In the Yang modes model, you always have a certain Lie group, G, which could be something very general. In physical applications, typically either SU2 or 3 or U2 or 3. So the special unitary group or the unitary group. And this kind of Abelian-Higgs model corresponds to the special case when this Lie group is given by U1. Okay. So just kind of the circle. Right? And U1 is, of course, Abelian, and that's where the model gets its name from. Right? So it's the special case of Yang modes with an Abelian group G. Right? So it's kind of where the name comes from. So I hope everybody feels sufficiently motivated. So I could maybe stop for a second and see if anyone has a question. Otherwise, I'll tell you about some of the results.
Yeah. What is the role of the Leray projection in the?
So it's the one that keeps you in the Coulomb gauge. Okay. Right? So we had this condition that delta J Aj is equal to 0.
Yeah, that's the answer I was looking for.
Yes. Yeah, so without this, this wouldn't be here. Okay, so let's talk about some of the results. So the first things I want to mention is about the local opposing of these models. And let me start with the message. The message you should take away from this slide is that the local opposedness, at least now, is very well understood. So there's different approaches you can take. The first one is, this approach that's called regularity structures that was initially developed by Martin Heirer. So Martin Heirer developed, together with many of his collaborators, this very general theory, which is called regularity structures, which also led to his Fields Medal in 2014. And this is a very general theory that can treat many different singular SPDs, and it has also been applied to these kind of models. So it was first applied by Hao Chen to exactly this kind of model that we care about, this Abelian-Higgs model in dimension 2. And a little bit later, Chen, together with Chandra, Cherev, and Heirer, then treated this more general Yang-Mills-Higgs model, also in dimension 2. Right? So the same kind of regularity, but more difficult because the Lie group is more complicated. And even later, the same set of authors then studied this Yang-Mills-Higgs model in dimension 3. Right? So let me remind you that the higher the dimension, the more difficult this model, because the regularity of the space-time white noise decreases in the dimension. Right? So in dimension 2, it's -2. In dimension 3, it's -5/2, which is a fair bit lower. So at some point, Sky Kao and I were both at the IS, and we wanted to understand this kind of paper here, this Chandra Cherev Heirer paper. But neither one of us was an expert on regularity structures. Since then, actually, we've learned a bit, but especially when we started reading this, we were not expert on regularity structures. So when we were reading this, it was very helpful for us to translate this into a slightly different language, because there are actually other approaches to singular SPDs that are maybe slightly less general, but a bit more hands-on. Right? So one of these approaches is a theory called pair-control calculus that was developed by Gubinelli, Imker, and Napakovsky. And if you know a little bit of harmonic analysis, this one is very easy to pick up. So at least for somebody like me, that was much easier to learn. Again, it's maybe slightly less general, but it's much closer to what one is typically used to. So we kind of we proved a lot of the results of this kind of paper using this other machinery. And at least for us, this was very useful. And then we thought other people might find it useful as well. So we actually turned this into a paper. What one should say very briefly is that these papers, they don't just prove local oppositeness, they prove a few other things. For instance, in the Yang-Mills setting, it's not so clear that the solution theory developed is gauge covariant, because there you can't quite fix the gauge. And that's one thing you have to prove as well. But I don't want to get so far into this. So it's a bit more than local oppositeness, but at the end of the day, everything here is on a short time interval. That's why I call it local. So the next step is then, of course, the question of global oppositeness. And the message that I want you to take away here is that the global oppositeness is not well understood at all. Okay. So the reason is because it has to be equation specific, right? So regularity structures applies to a very general class of equations, but global theory, of course, is much more equation specific. So prior to our work, there was only one result, which is a result of Cherev and Chen. And they proved the global oppositeness and invariance of the Gibbs measure for pure Yang-Mills in dimension 2. So here I'm stressing this word pure because the result only applies to the Yang-Mills model, the one we only have the A. It doesn't apply if you include a scalar field. So if you have the phi, the method no longer works. So this paper is, I think, a really major breakthrough in the field. It introduced a lot of new ideas and combined them with many of the existing, heavy machinery. The one thing that it uses that maybe I actually know best is an argument that was first used in nonlinear dispersive equations, which is actually where I was trained. And this is a method that's called Bjoern's globalization argument. And this was first introduced actually for nonlinear Schrödinger equations. And roughly speaking, it's a method that allows you to globalize your solutions to these kind of singular SPEs, provided that you already know a lot of information about the Gibbs measure. So for this Yang-Mills model, for the pure one, we actually already understand this Yang-Mills measure pretty well. The reason is that it's something that I would call completely integrable. So in 2D, in the pure Yang-Mills case, it's more or less completely integrable. So this measure is actually very well understood, and we even have very nice moment estimates for the measure. And if you then combine these moment estimates with Bjoern's globalization argument, you can prove the global oppositeness. So it's a very nice paper, but this is kind of the main drawback, because for many of the other models that one cares about, we do not yet know the measure, right? Because remember, we want to do stochastic quantization. We want to use the equation to understand the measure. And this is, for instance, what limits it to the pure Yang-Mills model. Once you add the Higgs field, the information about the measure is no longer known, and therefore you cannot really use this Boolean globalization argument. Right? So what we wanted to do is to prove a global result, but without using this argument. So that's the result that this talk is about. So this is a theorem that I proved with Sky Cow. It's stated a bit informally. But what it tells you is this stochastic Abelian-Higgs model, which we have here, at least in dimension 2, is globally well-posed. And furthermore, the solution, A and phi, obeys uniform in time estimates. So you can look at the moments of your solution, and you can let t go into infinity, and they'll stay bounded uniformly in time. Okay, so there's no growth whatsoever. So let me make a small number of remarks about this result. So first of all, as I already said, we do not use Boolean's globalization argument. Right? And as a result, we do not need any information whatsoever about this Abelian-Higgs measure. So the Abelian-Higgs measure has actually been constructed by the constructor quantum field theory community, but we do not rely on this construction at all. Okay? We only use PDE arguments, some of which I'll be able to tell you about in the later part of this talk. Because of this, you can actually use our theorem as the main step towards a new PDE construction of this Abelian-Higgs measure. So you can actually use the result to construct the measure, which is very much in the spirit of stochastic quantization. The reason why I'm saying main step is because the paper is missing about 15 to 20 pages if you actually want to go through this construction. It's very standard. I think all of the steps are in the literature. We just didn't do it because the paper is already 100 pages long, and we felt like adding 20 more, for this would not necessarily be justified. In any case, I think the theorem in and of itself is of interest, right? Even if you put this construction of the measure aside, because it's a nice global well-posedness result. And I think at least in this room, I don't necessarily have to justify why you would like to prove global well-posedness of a PDE. I think this is hopefully okay. And, otherwise, I presume half of you are out of a job. So let's take that for granted. Yeah.
What's the regularity of the initial phi?
So that's not so important, but you wanted to have the regularity of the samples of the measure. So here you would have regularity kind of minus epsilon. But because it's a parabolic equation, some of the regularity of the initial data is not so important. What's more important is the regularity of the forcing, because that kind of stays with you.
So then dAj and dA comma j is actually a parabolic.
Yes, yeah. So this here is the normal heat operator. And this here is also a heat operator, but kind of built out of this covariant way. So it's sometimes called the covariant Laplacian, and I'll actually call it this a bit later. And it's sometimes called the magnetic Laplacian. It's kind of the Laplacian of the magnetic field. Right. So this is this parabolic. Any other questions about the result? Yeah.
So how about the syntactic behavior? Do you know anything about?
So what you would hope is ergodicity. So you would think that it should be ergodic, but I am not the best person to ask about this. I mean, there are many results like this in the literature actually, but we haven't tried for this model specifically. Okay, so then let's go into kind of the argument. And let me first give you a very quick view of the local theory, or a recap. So in the local theory, you always follow kind of a non-covariant approach or non-covariant philosophy. So what this means is that in the local theory, you view these covariant derivatives, dAj, as perturbations of delta j, right? So you look at this covariant derivative, which is still written somewhere there, and you say that this iAj phi term is a zeros-order term in phi, therefore it's kind of less important, so I'll just try to treat it perturbatively. So with that philosophy in mind, let me slightly rewrite this stochastic Abelian-Higgs model. So in the first equation, all I did was I took this Laplacian of A and I put it on the left-hand side, just to indicate this is something that I do not treat perturbatively, right? So everything that's on the left-hand side, I don't treat perturbatively. Everything that's on the right, I try to treat perturbatively. Right? Now, in the second equation, I'm doing a slightly more invasive reformulation, right? If you view these kind of covariant derivatives as perturbations of the usual derivatives. It makes sense to review this covariant Laplacian as a perturbation of the usual Laplacian. And therefore, you might subtract the usual Laplacian acting on phi from both sides of the equation. Right? Now you have kind of the same differential operator on the left-hand side as the one that you have here, right? But one that you understand, of course, very well. And on the right-hand side, you have this, but this does not contain any second-order terms in phi. Right? It only contains first-order terms in phi. So you might think, okay, that should be better. Okay, so now you have this. And what do you not do? The thing you do in this business is you always introduce certain stochastic objects, right? So the regularity of the forcing is way too low that you could make sense of all of this deterministically. You somehow have to use the randomness. And to use the randomness, you want to introduce certain stochastic objects, which you can understand better. The simplest ones are these kind of linear stochastic objects here. And what they are supposed to do is they're just supposed to solve the heat equation with these kind of stochastic terms on the right-hand side. So you have this first thing right here, which is typically noted using this lollipop notation, this kind of a diagrammatic notation. The dot here, this half dot, stands for the noise, and this line here stands for the Duhamel integral that you get from integrating the equation. And then you're just solving the heat equation with the stochastic forcing term on the right-hand side, right, the one from here. And let's say the initial data of this we just set to 0. So you're trying to really absorb this lowest regularity term here. And then you define this other lollipop, which has the full dot the same way, but with the other stochastic forcing, with the theta. Right? So I'm using this kind of half dot and this full dot here just to keep track of which noise this object corresponds to, right? Because I have two different ones. And if this is the first time you're seeing it, the notation maybe looks very funny, but it becomes very useful if you look at higher order objects, right? So if you compute the next Picard turret, you would maybe get something like this. So this would be kind of the next Picard turret in the equation for phi, and you could iterate it even further and so on. So, you know, Picard turrets kind of, you can track using trees, and these are trees, right? So if it's just two of them, maybe it doesn't make that much sense to use it, but in the paper we have many, many more. So, okay, then it eventually pays off, right? So what is the regularity of these objects? Well, the stochastic forcings, they have regularity -1, minus dimension over 2, minus epsilon. Right? We're in dimension 2, so stochastic forcings have regularity -2, minus epsilon. And heat equations are supposed to gain two derivatives. So these lollipops are supposed to have regularity minus epsilon, so just barely negative. But that's, you know, that stays the same for all time, right? Because the stochastic forcing is stationary in time. It doesn't improve with time. So once you have these lollipops, you can think of yourself, well, you know, maybe I captured the roughest part of the solution. Let's make an ansatz which writes the A as the first lollipop plus the remainder Z, and the phi as the other lollipop plus the remainder psi, and you hope that Z and psi should be at least a little bit smoother than the A and phi itself. So now you can think, okay, what equations do Z and psi have to solve? This, of course, you can work out because you know the equations for A and phi, and you know the equations for the lollipops. And what you end up with is this. So for the Z, you see this kind of derivative nonlinearity that we had here, but I already inserted the ansatz for phi. Right? So I inserted what phi is into this equation right here. I didn't insert it for A because otherwise the expression gets a bit messy. It's in a subscript. And the stochastic forcing is of course gone, right? Because that's why I introduced the lollipop. Right? But there's still a lot of roughness here because the lollipops are not that smooth. And then I have this other remainder psi, which, you know, solves this equation. So again, the stochastic forcing is gone, but every phi has been replaced with the lollipop plus psi. So I have these things here. So even though, you know, Z and psi are supposed to be a bit smoother, it's still not really possible to solve this using a contraction mapping argument. You have to use more modern machinery. You can use either regularity structures or power control calculus. I could talk about this more, but this is a little bit orthogonal to the main points I want to make, because this is more about the local theory. So feel free to ask me about this after the talk, but I think this is as much as I want to say about this here. Right? So this is not trivial, but understood. So, okay, let me give you now a first glimpse at the global theory. Right? So let's say you have these equations for Z and psi, and now you want to prove that not only are they locally well-posed, but actually globally well-posed. What's the first thing you try? Well, you try to use some kind of energy or some kind of monotonicity formula or something like this. right? It's very difficult to use the energy of the equation itself, this E that we still have here, because the E requires very, very high regularity, right? And even worse, the good term in the monotonicity formula for E requires even more regularity. So E has regularity 1, but the good term in the monotonicity formula for E has regularity 2. That's much, much higher than the things we have on this slide. So both Z and psi will only have regularity 1 minus. So it's really hard to use this energy. What one can instead try to do is, well, psi solves the heat equation, right? So it's very natural to look at the derivative of the L2 norm, right? Typically, you have some nice formulas for that. So let's just try this, right? On the left-hand side, we had our usual Laplacian, right? So then you immediately pick up a good term, which has the usual gradient here. So there's a term that has a good sign, it's a plus, right? And then what you get on the right-hand side, you get the real part of an integral of psi bar against everything that appeared on the right-hand side in the equation for psi, right? One of the terms was exactly this kind of difference here between this covariant Laplacian and the Laplacian acting on the lollipop and the psi. And if you not try to treat this as a good term and you try to treat this as an error, eventually you have to estimate this difference of the Laplacians acting on the lollipop and this difference of the covariant and the usual Laplacian acting on the psi. And these are two things that you have to now estimate if you follow this approach. And the issue here is that if you try to estimate this, inevitably it's going to cost you factors of A, right? Because you're going to insert the definition of these covariant derivatives, and you're going to either in the remaining terms pick up one A and one derivative, or you're going to pick up two A's. So it's definitely going to cost you kind of factors of A, and that's just very costly. The reason is that the equation for A has very little that gives you any decay, right? So you have this Laplacian here, which is of course very nice and smoothing, but let's say you have some, low frequency part of A, then it really doesn't give you that much decay, right? And then this thing here doesn't really have any useful sign. So it's not hard to, that's really hard to use either. There's very little here in the equation for A that gives you any decay. It's unlike the equation for phi, where you have this nice cubic term that's helping you a lot. It's pushing you down very, very quickly. So we tried for several weeks or maybe a month to somehow make up for this loss of factors of A, because I didn't tell you how you try to estimate A. There's many things you could try, but none of them really worked. Okay. So at that point, you should reevaluate the choices you made in life that kind of got you here. And eventually you should realize that, okay, if I can't estimate this, maybe it's just not an error, right? I should not be treating this an error. I should be treating this non-perturbatively. So what this really means, I should be working more covariantly. Right? I should be working more directly with this covariant Laplacian. And of course, to the differential geometers in this room, this is very natural. Like they would never expand this covariant Laplacian in the first place. But you should really be careful here, right? Because you're not just trying to do differential geometry, which is already difficult, right? You're trying to combine it with, probabilistic and PD techniques. And just because something is nice from a differential geometric standpoint doesn't mean that it plays nicely with the probabilistic aspects of your argument. Right? So there's many reasons, probabilistically speaking, why you want to do this expansion, some of which I'll be able to tell you on the next slide. Right? So this sounds like a very easy idea, but it's actually really hard to pull off, right? Because of these other aspects of the argument. Okay. But that's kind of the starting point. So let's talk about covariant stochastic objects. Okay. So we made this decision to work more covariantly. Let's pick a connection 1 form B, which is time dependent. So you can think of this as our A, but I'll tell you at the end of the slide why we cannot choose it to be A. But if you want to, you can think from now of at least as this as being equal to A. But let's fix the connection 1 form. And then we can define this covariant lollipop right here. So this covariant stochastic object in the same way that we defined the black lollipop before, except that instead of the usual Laplacian, we're using this kind of covariant Laplacian, which is here. And if we have this, we can of course represent our stochastic object using the covariant heat kernel. So the heat kernel corresponding to this covariant heat operator, right? So I'm going to write my lollipop here as an integral, as a space-time integral, as of this covariant heat kernel against this space-time white noise. Right? So that I can always do. Right? And here's now the remark. For everything that I'm about to say, it is very important that this covariant heat kernel here and the zeta are probabilistically independent. So if you want to repeat some of the stochastic estimates, like the ones that are used in regularity structures or parametric calculus, you need this independence. Otherwise, these just don't work. But of course, that kind of prevents us from choosing B as being equal to A, right? Because, you know, phi depends on zeta, right? And A depends on phi. So clearly, A depends on zeta, right? And just notice here that you don't even have adaptedness, which often helps you in probability theory, because even though A is going to be adapted to the filtrations generated by psi and zeta, the heat kernel goes from the earlier time S to the later time T. So this is not going to be adapted to the filtration at time S, right? So adaptedness won't help you either, just as a comment for the probabilist here. So let me postpone for a second how we're going to choose this B. Let's just say B is fixed for now. And let's just decide that, you know, maybe these things are a good thing to study. And these are actually going to be helpful later. So what can you prove about these covariant stochastic objects? So here's a theorem that we use in the proof of the main theorem, but that I actually think is of independent interest as well. So let's pick B to be deterministic. And now what can we say about this lollipop, right? That is covariant lollipop. The first estimate that we have here is an estimate of the CT0 Cx minus epsilon norm, which is the natural norm in which one should be estimating this object. And we can control the pth moment of this object by square root of p times 1 plus the size of b to the 2 epsilon, where the size of b here is measured with respect to a suitable norm. So I don't want to tell you what the norm is. It's really not that bad, but it also doesn't fit on one line of the slide. And it's not the main point here, okay? The main point here is that you only need an epsilon power, right? You need very little of your b. The other thing that we can estimate here, modular renormalizations terms that I told you I would ignore, is this kind of derivative nonlinearity, right? So if you want to use this theorem to eventually prove the well-posedness of this Abelian-Higgs model, at some point you have to control this guy right here, this derivative nonlinearity. And you actually want to control the Duhamel integral of this. And it's the Duhamel integral with respect to the usual heat kernel, because here we have the usual Laplacian, right? So you have this Duhamel integral of this derivative nonlinearity here. And the natural regularity here is CT0 Cx 1 minus epsilon, because you have 0 minus 1, and then you're supposed to gain 2. And this you can estimate as well. And this time you're going to need slightly more than half a power of b. So no longer epsilon power, but also not that bad, just half power. So the thing I really want to highlight here is that it is really important for us that these estimates are sublinear in B. So in fact, just sublinear wouldn't be enough for us because there are other inefficiencies somewhere else in the argument. But this is kind of, with some modifications, good enough for us, right? And if you want these kind of sublinear bounds, it's something you couldn't possibly prove using perturbative arguments, right? Because if you ever insert the definition of this dB, you're going to have one factor of b, and well, then you're going to lose one power, right? So you really have to work kind of covariantly if you want to get something like this. So that's kind of what we can say about these covariant stochastic objects. So yeah, it is completely hopeless for me to show the full proof of this in this talk, and it would just be a very bad idea. But I have 2 slides that are supposed to convey some of the ingredients. So let me try at least that, right? So when you try to prove the second estimate right here, you're going to end up with an expression that looks like this, okay? So I don't expect you to be able to derive this in your head in the talk. That would be completely unreasonable. But let me just highlight the kind of aspects here that relate to the model that we had before. So this first P here is the usual heat kernel, the one for the usual Laplacian. That appears because we had the Duhamel integral on the right hand on the last slide, right? Then I have one PB here, which is the covariant heat kernel. That is because we had one covariant stochastic object. And then I have a dBPB, so covariant derivative of a covariant heat kernel, because I had one dB lollipop B, right? So this is the Duhamel integral, this is the lollipop, and this is the derivative of the lollipop, right? So you end up with something like this, where you integrate over S and Y and T and X, which are arguments here. So again, I don't expect you to be able to derive exactly this in your head, but hopefully it seems reasonable that something like this shows up quite naturally in the proof, right? There's only 2 things I want to highlight about this expression. The first one is, it actually involves covariant derivative of the heat kernel, not just the kernel itself, The kernel itself is actually quite easy to estimate here. You can use what is called the diamagnetic inequality. But if you want to control the derivative of the kernel, that's much harder. The other thing I want to highlight is that, as far as we're aware, these have not really appeared in the literature before, which is a bit surprising because a lot of people have studied heat kernels, right? So the reason why I think that is because, well, first of all, this appears very naturally if you study these random problems, but I don't know why you would study this if you only look at deterministic problems, right? So this is maybe why people haven't looked at it so much before. The other reason why they maybe haven't appeared before is because we really care about how our estimates depend on the size of B. But that's typically that doesn't happen, when you study heat kernels. When you study heat kernels, typically you have some kind of fixed Riemannian manifold or some kind of fixed connection one form or something. And that's just something that's given. So you don't typically track its size. Whereas we really care about that, right? Because we need that to prove global well-posedness. For I would be happy to be proven wrong and somebody tell me, these are very well known, they're in this kind of, Russian paper from the 80s or something. But we had to derive them from ourselves. We couldn't find it. Yeah.
So technically speaking, you're only controlling 1 minus epsilon derivatives, right?
Yeah.
Can you control one full derivative as using the same?
So that's not going to be true. You're always going to lose an epsilon when you do these random things. Is your question like you have cx1 minus epsilon rather than cx1?
No, I meant you can put more weight on the right hand side.
More weight on the right hand side. No, so even if you make B like smoother and you make it like of size 1, the object will never be any better than 1 minus epsilon because it's determined by the regularity of the stochastic forcing. Right. So even if B gets nicer, the regularity is never going to improve. Even for B equals 0, it's just that. Was that the question?
No, but that answered it.
Okay. So then one slide about what do you do with this, right? So how do you get control of that? And then I think I'll be able to finish in like 5 minutes. If that's good. Okay. So how do you control this? So we rely on covariant monotonicity formulas, and we got them from a paper of Hamilton. So this is the Ritchie Flo Hamilton. He wrote a very nice paper called Geometric Monotonicity Formulas somewhere in the 90s. And it's not in there exactly like this, but once you read the paper, you come up with it pretty quickly. So what is happening here? So this is very general. So take a solution var phi of an inhomogeneous version of this covariant heat equation, and take a k, which is a solution of a backwards heat equation. And this is typically non-negative, or at least whenever we use it, it's non-negative. And then you get this very nice monotonicity formula, which I wrote down here. So you can look at the time derivative of k times the square of phi. And what you get is k times the Laplacian of phi squared. And what is nice here is that you get the normal Laplacian, not the covariant Laplacian. Right? Even though phi itself solves the covariant heat equation. That may seem a bit surprising at first, but it's actually very natural because the absolute value squared is gauge invariant. So that's why you can act on it with the usual Laplacian. The second term is the one where it looks similar, but where the Laplacian hits k. And that's very nice because once you integrate this, these now cancel. Okay. And then the star of the show is this term right here, where you get this size of this covariant derivative, and you get it with a good sign. So this gives you a lot of control. And then at some point, you get the g. So this is really kind of the main thing we use to control this covariant derivative of phi here. And once you can control covariant derivatives of solutions to this inhomogeneous equation, you can use it to get some control of these kernels, right? So this is kind of 30 pages of the paper put on one slide, but more or less that's kind of the gist of it. So now you might ask, okay, how do I put all of this together? Let's get back to the nonlinear problem. That's only 2 slides and then we're done. So we work on time intervals. So I pick some t0 greater than or equal than 0, and I'm going to work on an interval that goes from t0 to t0 plus tau to some later time. Right? And this tau here is going to be small, but it will have to be chosen very, very carefully. So it's not the one from the local theory. So how do we choose this b that I can dance around a little bit? So I told you can't choose it to be a, but what you can do is you can take the initial data, a of t0, and then you can evolve that linearly under the heat flow. And the reason why that is a good idea is because this is going to be independent, not of all of the stochastic forcing, but at least of the stochastic forcing on the interval that you currently care about, right? Because A is adapted, so it's only dependent on the noise in the past, And this is the noise of the next interval, right? So you have independence here, which is the thing that you really want. And once you have that, at least morally, you make an answer that looks like this. You're going to write A as this B plus a lollipop plus a remainder. And you're going to write phi as this covariant stochastic object, but you find not with respect to A, but with respect to B. And psi, okay? But the actual answer in the paper looks much different. It has many, many more terms, but these are the main ones. Okay, so if you open the paper, don't be scared. This is the main thing. And the rest is, well, junk that you eventually have to deal with. Okay, so how do you know put everything together? Okay, so we can estimate B, right? Because that's just the linear heat flow. We can estimate the two lollipops because that's we already talked about. You still have to estimate Z and psi. We want to estimate psi using these covariant monotonicity formulas that I mentioned earlier. These are actually very flexible, and you can use these for nonlinear equations as well. We want to estimate Z, not really using any monotonicity formula at all. We're just going to plug into our estimates for this covariant lollipop and our estimates for psi. We're just going to combine them with the usual Schauder estimates that you have for the usual heat operator. Right, so this is roughly how we want to estimate these two guys. What do we want to achieve with these estimates? You want some kind of decay. So you want that on this interval already, you have a little bit of decay, so then you can iterate the thing. Right? Because if you get growth, well, your iteration might stop after a finite number of steps. Right? So here we want decay. So how do we want to get this decay? The thing that makes, B decay is just this heat flow. So you want that on this Timmer interval, this heat flow leads to significant decay of B. And I'm being purposely vague on what significant means, but it should be, well, noticeable. You want that this cubic term, which appears in the equation for psi, which would be here, leads to a very significant decay of psi. So this covariant Laplacian here gives you smoothing, but it doesn't really give you that much decay. What you really want to leverage is this cubic term here, which pushes large things down very, very quickly. And then the last thing you want is that you have this remainder Z, which you're not really estimating using any kind of monotonicity formulas. And you want that the estimates you have for this can be closed. Right? And you want, of course, that this stays small because it's supposed to be kind of a small remainder. So these are somewhat contradictory. For the first two, you would like tau to be somewhat large because you want to see decay. For the last one, you want tau to be somewhat small because you want to close your estimates. And it's not at all obvious that this works. Right? But if you're very careful, you can make it work. And you have to choose tau to be about this. So you have to choose about minus 3/4 of the size of A, and you have to choose about minus 5/2 of the size of phi. Right? So the way you actually do this in the paper is you write down two numbers, and then you get 7 or 8 conditions of these two numbers. And at the end, you're going to be very happy that there is a way to satisfy all of these conditions. Maybe just one last story. This gets much easier if you don't do cubic, but you do something higher. So if you do quintic, septic, or so on, you get something that pushes you down even quicker. So once we had this idea to work with these covariant stochastic objects, it was very clear to us that the argument would work if you just take a large enough power. So like 7, 9 or something. And then we kept optimizing the argument, and we eventually were able to do 3 here, which is the one that physicists care about, so then we were happy. Right? Yeah, so let me end here.
So, questions or comments? Would you like to take a stab at explaining how this connects with physics?
Yes. Okay. So, there's this very famous, let's say, Yang-Mills Millennium problem, which is typically about, let's say, quantum field theories. And these are typically phrased in terms of Minkowski space. So where like time plays a different role than space. However, there's this thing called a Rig rotation, which kind of turns the time into I times the time and turns your Minkowski space into Euclidean space. And when you do that, you turn this kind of quantum field theory in Minkowski space into a Euclidean quantum field theory. And there are these axioms called Osterwalder-Schroeder axioms, which if you prove these for the Euclidean quantum field theory, there's a general theory that tells you, oh, actually now you can define a Minkowski one. So you can rephrase this Millennium problem equivalently in terms of a Euclidean field theory. And basically what we did is we solved half the Millennium problem, except that dimension 4 is not 4, but 2. Yang-Mills is not Yang-Mills, but Abelian-Higgs. and the Euclidean space is not the Euclidean space, but the torus. And it's also only half. So we did not address the mass gap, which would be ergodicity, which was already asked about. So there were a lot of simplifications here. The most stringent one being going from dimension 4 to dimension 2. But you know, it's a millennium problem. So partial progress is still valid progress, I think.
Interesting.
Yeah.
Are other types of noises physically relevant?
So if you add other types of noises here, the thing no longer comes from a gauge invariant model. And that's something people don't like, right? So I think you always want to start with a model. So I didn't do this here, I wrote down the one in the gauge immediately, but you can start and write down the gauge invariant one first and then go into the gauge. And I think that's something that, you know, physicists would care very much about. And you actually also see the proof. So I think in these kind of models, you always want to do space-time white noise, at least most of the time. Of course, you know, if you want to just make progress towards a more difficult model and you can't get all the way there, okay, then it makes sense to maybe do, you know, dimension 3, but maybe not space-time white noise, maybe, you know, slightly smoother noise. So, but then I would really see it as kind of partial progress towards a physical model.
Any other questions or comments? Then it's time Bjoern again. Wow, you covered a lot.